Alright guys, here's part 2 of your video that's starting ionic compounds and ionic bonding, which is fantastic because you've already been learning it, you just didn't know you were learning it. I have attached the PowerPoint slides that go along with this, so if you just follow along with them, it will start talking about ionic bonds or ionic compounds. So first slide, just a title that says ionic bonds because they're fantastic. Next slide, part A. So we're breaking this up into two pieces. The first part is I want you to understand how ionic bonding works, and we're going to look at it through multiple ways. Another portion of this part is that you're going to learn how to draw Lewis structures, which are really simple, very, very easy. And then we're also just going to talk about the idea of a stable octet. So next slide, or third slide, is where we start talking about chemical bonds. And you know that a chemical bond is just the force that holds two atoms together. So I don't want you to think that there are two atoms and these atoms are connected by something or by like a stick. So I have two bobby pins here and they're not, you know, here they're connected actually physically by a stick. But they are not in a bond, and I just broke my Promethean pin. Hold on one second, guys. Okay, fixed it. In a chemical bond, there's just a force that's holding these two things in place together. So I don't see something here, but there is something there that's holding them together. So it's kind of like two magnets. You holding them really close and you can feel that there's a force that's attracting them together. But you don't see that force, you can feel it though. So it's that same idea. So when there's two atoms that are bonded together, they are not physically bonded together by like something. That's a force that is holding them in place. It is a force that's holding them together, okay? So a chemical bond, simply a force that holds two or three or four, however many atoms together. Now, chemical bonds, this force is typically an attractive force. So we think about it as an attraction between this positive nucleus and then all of the negative electrons that surround the atom. It's very similar to that. So think about chemical bonds happen because of the attractions between electrons and protons, or the nucleus. So the next slide, slide number 4, talks about valence electrons. You have already learned valence electrons and we already know what these mean. Valence electrons are the electrons that are on that outermost ring or in the outermost energy level of an atom. So these are the ones, these valence electrons are the ones that really do the bonding in chemical reactions. So how can we find a charge on an element thinking about their valence electrons? And you've already done this as well. So for example, on the next slide, I wrote out the electron configuration for sodium. So you know that's 1s2, 2s2, 2p6, 3s1. That's the longhand electron configuration for sodium. You know that looking at your periodic table, sodium has how many valence electrons? If you forget, we could draw Bohr's model. I have Na, it's in the third row, so it's going to have 3 rings, 2 electrons on the first ring, 8 on the second, 1 on that outer ring. So that means that sodium has 1 valence electron, so I just have 1 valence electron for sodium. I also could have looked at this and saw that if I wrote the noble gas version of this, it would have been Ne, because that's the last noble gas that sodium passed, and then it'd be, oh, I really messed that up, guys, 3s1. Forget this little scribble here, because that's just me messing up. So neon, and then 3s1. So I can look at this and see there's only 1 valence electron, because noble gas represents the core electrons, and whatever I write out represents the valence electrons. And since I only have 1 in this superscript here, that means I only have 1 electron. So 1 valence electron. Now, looking at Bohr's model, I want to get sodium to have a full outer shell. I can do that in 2 different ways. Sodium could gain 7 electrons to fill that outer ring, or it could get rid of this 1 and then it could be left with a full outer shell. So which one would it rather do? Would it rather lose 1 or gain 7? It would rather lose 1 because then it doesn't need as much energy. So what will happen if it loses this electron will leave, that whole outer ring disappears. Now if I look at this outer ring, I see that it's full. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons on it. Now if I changed my electron configuration, I would get rid of the 3s1. So now I'm just left with a noble gas, which is stable and has a full outer shell. So if I did that for the longhand, again, I'd get rid of that. Perfect. So now sodium only has 10 electrons here, and it has 11 protons. So what's its charge? I have one more positive charge than I do a negative charge, so sodium would be a +1 charge. You've created an ion, which is just a charged particle. There's 2 different types of ions. There's a cation, and then there's something called an anion. A cation is a positively charged particle. How I remember this is the T in cation represents a plus sign. So you can think that that T, because it represents a plus, indicates that a cation is a positively charged ion or a positively charged particle. So sodium has a +1 charge. That means it would be a cation. So I call sodium with a +1 charge a cation. Cations are formed when a neutral element loses an electron, which is exactly what happened here. Sodium had 1 extra valence electron on its outermost shell, but it gave it away so that way it could have now a full shell. So it lost an electron, which gave it this positive charge because now it has more protons than it does electrons. So this would be an example of a cation. Now, cations again are just positively charged ions. So what I want you to understand is would metals typically be cations or would nonmetals typically be cations? And if you think about this, metals are typically on which side of the periodic table? The right side. The left side. The metals are typically on the left side of the periodic table, and the nonmetals are typically on the right side. The nonmetals, do they want to gain electrons or do they want to lose electrons? Nonmetals want to gain electrons. So if they're gaining, they're going to have more of a negative charge. But cations have to have a positive charge. So nonmetals aren't cations. Metals are typically cations. And think about it. Sodium is a metal, and sodium wants to lose that 1 electron so it can have a positive charge. So it can have this full outer shell. So because it wants to lose an electron, it becomes positively charged, which makes it a cation. Now, if we, I want to skip, guys, to where it says a negative ion, which is an anion. And an anion is formed typically by nonmetals. So an anion is a negatively charged particle or a negatively charged element. So let's look at chlorine. Chlorine, what does it want to do? Does it want to gain an electron or does it want to lose 7? Wants to gain 1. So chlorine wants to gain 1 more electron. If it gains an electron, what charge would it have? It would have a -1 charge. Because it gained an electron, it gains more negative charges. That is considered then an anion. So any element that has a negative charge to it is called an anion. A way that you can remember this is really cool. So an anion stands for a negative ion. So you can remember an anion as a negative ion. So cation, you know, has that T in there, which represents that plus sign, so it's positive. And anion really just stands for a negatively charged element, which is a negative ion, or anion. So that's kind of a little helpful hint there. And typically, again, anions are nonmetals. So cations are positive, they are metals. Anions are negative, and they are nonmetals. So I want to tomorrow talk a little bit more about those slides that we skipped on slides 9, 10, and 11, which have to do with Lewis dot structures. So we'll do that tomorrow in class. Again, if you guys have any questions on anything that you've heard or seen, just let me know and post those questions on the blog. If you want to email me those questions because you don't want to post the questions on the blog, please feel free. And if you don't have any questions because you're super awesome and you just understand it all, that's great. I'll see you tomorrow. Have a good night. Bye, guys.